Gravity is holding you to your chair right now. It is keeping the moon from drifting into the void. It is bending light from galaxies 13 billion light years away so precisely that we can photograph it. We have measured gravity well enough to land a rover on Mars within a target zone the size of a football field. We have built entire civilizations on our understanding of it, and we have absolutely no idea what it actually is. Every other force in nature has a particle. Electromagnetism has the photon. The strong nuclear force has gluons. The weak force has the W and Z bosons. These are not just theoretical conveniences. We've detected them, collided them, built technologies from them. The Standard Model, the most precisely tested theory in the history of science, accounts for 3 of the 4 fundamental forces through particles. Gravity stands alone. No particle, no quantum description, nothing. Here is what makes this deeply unsettling. This is not a gap at the edge of our knowledge. This is a gap at the very center of it. The force you are feeling in your body right now, the force that shaped every star, every galaxy, every structure in the observable universe, it exists completely outside our best framework for understanding reality. Subscribe if you want to follow this search for the final missing piece of existence. Now let us begin. To understand why finding gravity's particle is so difficult, you first need to understand the 2 great empires of modern physics and why they cannot share a throne. The first empire is quantum field theory. This is the framework that governs everything small: atoms, electrons, the nucleus at the center of every cell in your body. In this picture, forces are not invisible pushes and pulls acting at a distance. They are conversations between particles carried by messenger particles exchanged back and forth. Electromagnetism works because charged particles toss photons between each other. The strong force works because quarks exchange gluons. Think of it like 2 ice skaters throwing a heavy ball back and forth. The exchange of momentum is what pushes them apart. The force emerges from the particle exchange. This framework, the Standard Model, has been tested to 12 decimal places. It is arguably the most successful scientific theory ever constructed. The second empire is general relativity. This governs everything large. Planets, stars, galaxies, the large-scale structure of the entire universe. Einstein's insight was radical. Gravity is not a force at all in the conventional sense. It is the geometry of space-time itself. Mass and energy warp the fabric of space and time, and everything else simply follows those curves. Place a bowling ball on a stretched rubber sheet and watch it sink. Nearby objects roll toward the depression, not because something is pulling them, but because the geometry of the surface has changed. General relativity predicted black holes before we believed they existed, predicted gravitational waves a century before we detected them in 2015, and remains unchallenged at every scale where we can test it. Here is the problem. These 2 empires speak entirely different languages. Quantum field theory is built on discreteness, probability, and fundamental randomness. General relativity is built on smooth, continuous geometry, determinism, and elegant curves. When you try to translate one into the language of the other, the mathematics does not just struggle, it breaks completely, catastrophically. And the universe does not care that our 2 best theories are incompatible. It simply keeps running on rules we have not yet found. So physicists did what physicists do when facing an impossible problem. They followed the pattern that had worked every single time before. When Maxwell wrote down his equations for electromagnetism in the 1860s, gravity looked similar in important ways. Both forces weakened with the square of distance. Both extended infinitely through space. Both had a field strength at every point in the universe. So the logical question became, if we could take electromagnetism, apply the rules of quantum mechanics to it, and extract the photon, what happens when we do the exact same thing to gravity? The process is called quantization. You take a classical field, identify its oscillation modes, and those modes become particles. For the electromagnetic field, this gives you the photon. For the field that carries the strong nuclear force, this gives you gluons. For the weak force fields, this gives you the W and Z bosons. Each time physicists ran this procedure on a force of nature, a particle came out the other end. The Standard Model was built one quantization at a time. Gravity has a field. It has a strength at every point in space. It supports waves, gravitational waves that travel at the speed of light, just as electromagnetic waves do. Every ingredient is present. Run the quantization procedure on the gravitational field and something comes out. Physicists call it the graviton. Now, here is what is remarkable. You do not get to choose what the graviton looks like. The mathematics dictates it entirely. If the graviton exists, it must be massless because gravity has infinite range, just like electromagnetism, and massless particles are what produce infinite range forces. It must travel at the speed of light. And critically, it must be what physicists call a spin-2 boson. This is not an assumption or a preference. It is the only type of particle mathematically capable of reproducing Einstein's field equations in the classical limit. Any other spin value produces the wrong physics. This is why the graviton feels almost inevitable. It is not a particle someone invented to fill a gap. It is the particle the mathematics demands must exist if gravity works the way we think it does. And we have indirect evidence pointing in this direction. In 2015, LIGO detected gravitational waves for the first time, ripples in spacetime from two merging black holes over 1 billion light years away. If the graviton is real, then that gravitational wave was not just a ripple. It was a coherent flood of gravitons in the same way a laser beam is a coherent flood of photons. A single wave at LIGO's detection threshold would contain at least 10 to the power of 36 gravitons traveling together. We detected the wave. We felt the ocean. We just cannot find a single drop. Here's where the story turns. Because when physicists actually sat down and tried to build a complete quantum theory of gravity using the graviton, the mathematics did not just resist. It collapsed into something that can only be described as a catastrophe. To understand why, you need to understand a technique called renormalization. When physicists first tried to calculate precise predictions using quantum field theory, they kept running into the same problem. Certain calculations returned infinity as their answer. Not a very large number, actual infinity, which is obviously not a physically meaningful result. The universe does not contain infinite quantities of anything measurable. The solution, developed through the 1940s and refined since, is renormalization. Think of it this way. Imagine you are trying to calculate the exact bill at a restaurant, but your calculator keeps displaying an error every time a certain ingredient is included. Renormalization is the mathematical equivalent of saying, instead of calculating that ingredient from first principles, we simply measure its actual cost directly from the real world and plug that measured value in. The infinities get absorbed into a finite number of measured quantities, the actual mass of an electron, its actual charge, and the theory moves forward, producing extraordinarily precise predictions. The critical word there is finite. Renormalization only works if the number of infinities you need to absorb is finite, a manageable number of measured values to anchor your theory to reality. For quantum electrodynamics, this works beautifully. For the strong and weak forces, it works. The standard model is renormalizable, which is a large part of why it is so powerful. Now apply this to gravity, apply it to the graviton. The problem is unique to the graviton, and it comes from a single devastating property. The graviton carries energy. And in general relativity, energy creates gravity, which means gravitons gravitate. They interact with each other. A photon does not interact directly with other photons through electromagnetism. It interacts with charged particles, which then feed back on the field. That extra step limits the complexity of self-interactions, but a graviton can directly produce other virtual gravitons, which produce more virtual gravitons, which produce more endlessly with no limiting step in between. Instead of a finite number of infinities to absorb through renormalization, quantum gravity produces an infinite cascade of them. An infinite number of terms in the calculation, each requiring its own measured value to anchor it. You would need infinitely many experiments to pin down infinitely many parameters. The theory makes no predictions. It explains nothing. It is mathematically meaningless. Physicists call this non-renormalizability, and it is not a technical problem waiting for a cleverer calculation. Many of the brightest minds in theoretical physics spent decades attacking this from every angle. The conclusion kept coming back the same. This is also why the problem becomes most devastating precisely where it matters most. At the center of a black hole, gravity becomes infinitely strong. At the moment of the Big Bang, the entire observable universe was compressed into a region where quantum gravity effects dominate completely. These are the two moments in cosmic history where a theory of quantum gravity is not optional. It is the only thing that could possibly describe what is happening. And these are exactly the two places where our best attempt at such a theory produces pure nonsense. You are sitting in a universe born from a singularity that our mathematics cannot describe. Every atom in your body traces its origin to a moment that exists right now, completely outside the reach of our understanding. That is not a poetic exaggeration. That is the literal state of physics today. And if you think detecting the graviton experimentally might sidestep the theoretical problem, the universe has a separate answer prepared for that idea as well. Freeman Dyson argued in 2012 that the laws of physics appear almost deliberately arranged to prevent us from ever directly observing a single graviton. To isolate one using a detector sensitive enough to feel its effect, the detector itself would need to be so massive and so compact that it would collapse under its own gravity and become a black hole before the measurement could be completed. To generate gravitons in a particle collider the way we generated the Higgs boson, you would need a collider approximately 3 light years in diameter, larger than the distance from our sun to the nearest star. The mathematics breaks when we theorize it. The universe hides when we try to find it. Whatever gravity actually is at its deepest level, it is protecting that secret with extraordinary commitment. Step back from the equations for a moment. Right now, as you are watching this, approximately 100 trillion neutrinos are passing through your body every single second. They come from the sun, from cosmic rays, from the residual heat of the Big Bang itself. They pass through you, through the chair beneath you, through the entire planet Earth, as though none of it exists. You will never feel them. You cannot feel them. They interact so weakly with ordinary matter that most of them will travel through a light year of solid lead without touching a single atom. If gravitons exist and behave as the theory suggests, they are doing something similar. An uncountable flood of them streaming through you right now, through every structure you have ever stood inside, through every mountain and ocean floor, carrying the fundamental information of how space-time curves and passing through all of it completely undetected. Now consider this. You do not actually feel gravity pulling you downward. According to general relativity, what you are feeling right now is the floor accelerating upward into your feet. The Earth is constantly pushing you away from freefall. Freefall is the natural state. Sitting still is the strange one. The force you have felt in your body every moment of your entire life, the thing that has felt more constant and more certain than almost anything else you have ever experienced. We cannot explain what it fundamentally is. We cannot find its particle. We cannot write an equation that describes it completely. The most familiar thing in your existence remains, at its core, a mystery. To be fair to the full picture, the case for the graviton is not the only serious position held by serious physicists, and intellectual honesty demands we sit with the alternatives before drawing any conclusions. The first alternative comes from Roger Penrose, one of the most decorated mathematical physicists alive. Penrose argues that the entire project of quantizing gravity may be backwards. For decades, the assumption has been that quantum mechanics is the deeper theory, that general relativity must eventually be absorbed into a quantum framework. Penrose suggests the opposite. Perhaps quantum mechanics itself breaks down at the scale where gravity becomes significant. Perhaps the wave function collapse that sits at the unresolved heart of quantum mechanics is not a quantum phenomenon at all, but a gravitational one. In his view, we should not be quantizing gravity. We should be gravitizing the quantum, fitting quantum mechanics into general relativity rather than the other way around. This is not a fringe position. It is a serious research program with its own experimental proposals. History gives this humility some grounding. In 1917, Einstein added a term to his own field equations, the cosmological constant, because he believed the universe was static and eternal. When Edwin Hubble demonstrated in 1929 that the universe was expanding, Einstein called the cosmological constant the greatest mistake of his life. The most consequential physicist in history built an assumption into his greatest work that turned out to be wrong. If Einstein could be wrong about something that fundamental, the assumption that gravity must have a particle deserves genuine scrutiny. The second alternative is string theory. This framework was not originally designed to find the graviton. It began as an attempt to describe the strong nuclear force in the late 1960s. But when physicists examined its mathematics, a massless spin-2 particle kept appearing uninvited in the equations. The same particle that graviton theory demands must exist if gravity is quantum. String theory did not predict the graviton. It could not avoid it. That is either a profound hint or a remarkable coincidence, and physicists have disagreed about which for 50 years. The honest position is that string theory remains mathematically beautiful and experimentally unconfirmed after more than 5 decades of work. The third alternative is loop quantum gravity. Rather than replacing spacetime with strings, loop quantum gravity proposes that spacetime itself is granular at the smaller scales, woven from discrete quantum loops. Area and volume would have minimum possible values at the Planck scale, approximately 10 to the negative 35 meters. In this picture, the graviton is not a fundamental particle, but an emergent phenomenon, a collective ripple across the woven fabric. The way a sound wave is not itself an atom, but a pattern moving through atoms. Each of these paths leads somewhere genuinely different. Each has proponents who have dedicated their careers to it. None of them has won. The universe has not yet told us which language it prefers. That is not a failure of science. That is science working exactly as it should, holding multiple serious possibilities open until the evidence forces a decision. The search is not standing still. In 2035, the European Space Agency plans to launch LISA, the Laser Interferometer Space Antenna. Unlike LIGO, which sits on the ground and measures arm lengths of 4 kilometres, LISA will consist of 3 spacecraft flying in a triangular formation with arms 2.5 million kilometres long, drifting silently through space. At that scale, it will detect gravitational waves at frequencies LIGO cannot reach, waves from supermassive black hole mergers from the early universe itself. The data flowing back from LISA may carry fingerprints in the signal that only make sense if gravity has quantum structure. Not a direct detection of the graviton, but potentially the first observational evidence that the gravitational field behaves like a quantum field rather than a smooth classical one. Closer to the ground, a different class of experiments is taking shape. The Bosemer-Vedral proposal, developed in 2017, suggests a tabletop experiment using 2 tiny masses cooled near absolute zero, held in quantum superposition, interacting only through gravity. If those masses become quantum entangled through their gravitational interaction, that entanglement can only be explained if gravity itself is capable of mediating quantum information, which would mean gravity is quantum, which would mean the graviton, or something very much like it, must exist. This experiment has not yet been performed at the required precision, but it does not require a 3 light-year collider. It requires exquisite isolation from vibration and noise and quantum sensing technology that is advancing rapidly. The Einstein telescope, planned for construction in Europe later this decade, will be 100 times more sensitive than current LIGO detectors. It may detect gravitational wave signals carrying subtle deviations from classical general relativity, deviations that quantum gravity theories predict should appear at high enough precision. None of these experiments will hand us a graviton sitting in a detector like a photograph, but science rarely works that way. The electron was not seen. It was inferred. The Higgs boson was not watched. It was reconstructed from the debris of 10 billion collisions. Evidence accumulates, confidence builds, the picture sharpens. The next decade of gravitational physics may not answer the question, but it will almost certainly change the shape of it. We built telescopes that see 13 billion years into the past. We detected ripples in space-time smaller than 1,000th the width of a proton. We reconstructed the first fraction of a second after the Big Bang from the faint afterglow of ancient light still crossing the universe today, and the foundation beneath all of it, the force that shaped every structure in existence, the thing you have felt in your body every moment of your life without a single second of interruption, remains at its deepest level outside our reach. Maybe that boundary is technological. Maybe a civilization 1,000 years more advanced than ours detects gravitons routinely, the way we detect radio waves. Maybe that boundary is something more fundamental. Maybe the universe has a depth that perception by its very nature cannot access from the inside. Or maybe, and this is the possibility I find most worth sitting with, the right question has not been asked yet. Every genuine revolution in physics came not from answering the existing question better, but from realizing the question itself was wrong. Space-time was not discovered by improving Newtonian gravity. It required someone willing to question what time actually was. That question is waiting somewhere right now, possibly in a mind watching this. What do you think gravity actually is?